Hello everyone, I'm Ziwen, and the title of our article is KEPC-Push, a knowledge enhancement proactive content push strategy for age-assisted video feed streaming. Our team members are from Tsinghua University, ByteDance, and Peng labs. With the explosive growth of the video volume, the communication pressure in the backbone network is increasing. In order to alleviate the transmission pressure, the age-assisted video delivery method is widely adopted. As shown in the figure, instead of user directly accessing the CDN node, users now will be scheduled to a series of edge nodes nearby. Edge nodes can be in the gateway of a campus or a building, which are much closer to the users. In this way, the access latency can be further improved by at least a half to the level of 10 to 20 milliseconds. Since the bandwidth in an age-assisted video streaming system is charged by the peak time CDN bandwidth, video provider will often predict which video files will get high peak period popularity based on their historical access information, and proactive push popular peak period files in advance during the off-peak hours. In this way, the peak bandwidth transmission pressure can be significantly alleviated. Video feed streaming service such as TikTok, Reels, Qiao is becoming increasingly popular. In video feed streaming applications, users keep scrolling down and the applications will recommend users with video of users' interests. However, video feed streaming poses new challenges to which videos to catch in the CDN age architecture. This is because for video feed streaming applications, content providers need to push the freshed videos to attract the user's interests, where historical data is inaccessible. For example, in our measurement, as shown in the right figure, the median time between video upload by creator and the distribution to the users is around 20 hours in the video feed streaming, which is not enough to even gather the historical information from one day before. While for the video on-demand applications, the time could be days to weeks. The absence of historical data can lead to inaccurate popularity prediction and imprecise proactive video push, which in turn leads to observed load imbalance and mismatches. For example, the left figure shows that the connection failure ratio of requests increases rapidly during the peak period, and the highly skilled workload across different edge nodes limits the utilization of the edge network. The right figure shows that the geographical distribution of requests is unbalanced, which leads to inaccurate resource allocation and about half of all requests requiring cross-region scheduling. Compared with sum-region scheduling, cross-region user requests will degrade the user's quality of service. For example, download speed, the first packet RTT, and the packet loss rate. In summary, a practical proactive push mechanism faces the following challenges. Firstly, how to achieve load-balanced proactive push for heterogeneous edge nodes without sufficient historical information. And the second problem is that how to ensure that the scheduling scheme can satisfy systems requirements for large-scale video streaming service. To address the challenges, we propose the KEPC-Push, a knowledge enhancement proactive push strategy. Our main insight is that knowledge derived from the content features of video files, such as video category and duration, can provide additional information for determining video popularity trends during the cold start phase. Importantly, These features are obtained at the time of video creation and do not rely on historical data. Besides, a lightweight scheduling scheme is also necessary to ensure that the proactive content push can run in real time in the large-scale system. The figure shows a system overview of our scheme KEPC-Push, which can mitigate the load imbalance and allocation imprecise problems by introducing knowledge derived from the content features of video files. Specifically, two modules are designed to address the two challenges respectively. The first one is the file feature embedding module. To cope with the problem of insufficient historical information, we propose FFE module, which extracts the underlying popularity correlation of files from the content features and collaborative behaviors by utilizing knowledge graph and collaborative filtering algorithms, respectively. Second, to design a fine-grained and lightweight scheduling scheme for large-scale video feed streaming service, we propose the file deployment scheduling module, which allocates resources at the regional level and reduces the complexity of the proactive push problem with the help of a clustering-based deployment mechanism. Okay, to figure out which content features are related to popularity trends, we have done some experiments, and our data analysis uncovers some useful phenomena and identifies the content features that determine the popularity correlation between files. Firstly, we find that files created by the same author or belonging to the same video are more likely to have similar popularity trends. This is because when an author or a video becomes popular, other files created by that author or belonging to the video will also be requested more frequently. And secondly, the popularity of files can scale significantly in some characteristics, such as category, resolution, and duration. Thirdly, the files published at the time tend to reach peak popularity at similar times, so they should be stored separately in the H network. The above findings indicate that there is a strong correlation between the file popularity and some key content features, and the video files with similar content features should be stored separately on different H nodes to avoid too high or too low workloads in a short period of time. One consequence challenge is how to access the similarity of files on the aforementioned content features. Considering the success of knowledge graphs in understanding relations, we utilize the knowledge graph embedding method to learn representation vectors for different items. We choose 6 different content features, namely video ID, author, category, resolution, duration, and publication hour, to construct the knowledge graph based on the TransR model. And by mapping items and their attributes into the knowledge graph, a general and compact context can be provided. After the training process, we can get 128-dimensional representation vectors of all video files, and the distance between two vectors is inversely proportional to the popularity correlation of two files. Although the KG-based representation library has been acquired, new files are constantly being created during the proactive push process, and these files do not have corresponding vectors. So, How to handle constantly published new files during the push process? First of all, we calculate the hit ratio of the representation vectors in the KG-based representation library. If the hit ratio is too low, we will retrain the entire knowledge graph. Otherwise, we can supplement the missing representation vectors by collaborative filtering embedding technology. Specifically, the supplementary operation is divided into 5 steps. Step 1. Collect all user requests within 4 hours and count the frequency of video access. Step 2. Screen out video files that are accessed less frequently than a preset threshold. Step 3. Group requests into separated collections based on user differences. Step 4. Use the item-to-vector method and skip gram model to train the self-based representation vector library from the user access set. Step 5. Use the similarity of items in the self-based representation vector library to supplement the KG-based representation library. And as for the file deployment scheduling module, which completes the load balance the proactive push decisions, it should first determine how many replicas to push for each video and how much replaceable cache size each edge node should provide before each round of push. And to solve this problem, we design a region-level allocation mechanism which makes independent allocation decisions for each region. Firstly, we use ChargeBoost model to forecast the peak period popularity of videos in each region. The reason for predicting at the regional level is that different regions have different user bases and thus be interested in different contents. Secondly, to ensure that each request can be responded by at least multiple edge nodes to guarantee the QoE. The number of to be pushed replicas in each region can be calculated based on the predicted results and the network cache information. Thirdly, the replaceable cache size of each edge devices can be determined based on their storage size and bandwidth utilization. For example, the edge with larger cache space or lower bandwidth utilization will be allocated larger replaceable cache sizes, which help to evenly share the workload on different edge nodes. And then, how to match the to-be-pushed replica with the edge node based on the obtained representation library in a light. We first use K-means clustering algorithm to cluster video files based on their representation vectors and then complete the load balance proactive content push through 2 aspects. On the one hand, we use the deployment of replicas of video files with high predictive popularity. On the other hand, we know that files with close vector distance have similar popularity traits, which means they need to be strong separately to balance the load. Therefore, we select the appropriate cache device based on the distance between video vectors and the performance of edge nodes to cache files. In this way, the FDS module not only completes the load balance the proactive content push, but also reduces the computational complexity. And in the experiment setup, the dataset is collected with the help of Douyin, a leading online video sharing platform, and it consists of 3 components: client requests, file features, and device information. The client request data consists 16 million client traces spanning 3 weeks in September 2022. And to verify the performance of our proposed method, we build a trace-driven experiment platform, which can simulate parallel user requests based on the prepared traces. And in order to keep KEPC-Push and other baselines consistent with the online deployment environment, we set 5 minutes as a decision-making cycle, and the replica are pushed to the edge network only between 0 a.m. and 20 p.m. To evaluate the performance of our KEPC-Push, we choose some existing SOTA algorithms modified to proactive push strategies and use different metrics to validate performance improvement and challenge solution. For improvements in CDN bandwidth consumption and user experience, KEPC-Push saves the most CDN bandwidth, which indicates that KEPC-Push achieves excellent bandwidth-saving performance through the knowledge enhancement proactive content push strategy. And KEPC-Push improves the average download speed of user requests and reduces connection failure ratio. The improvements not only to ensure the smooth of user viewing, but also to avoid requests being redirected to CDN due to insufficient transmission capability. For improvements in load balancing performance, KEPC-Push reduced the ratio of overloaded nodes, especially during the evening peak period. The overall bandwidth utilization of KEPC-Push is higher than other algorithms during the whole day, and KEPC-Push achieves the transfer of access traffic from high-load nodes to low-load nodes through appropriate cache setting. As for the improvements in file allocation and cache hit performance, KEPC-Push can reduce the cross-region request ratio by about 8%, which means that more user requests can be served by edge nodes in the same region, shortening the communication distance. And KEPC-Push can significantly reduce the number of replicas pushed because precise resource allocation increases the cache lifetime of valuable files, reducing the number of replicas deployed repeatedly. Besides, KEPC-Push's cache hit performance consistently outperforms other algorithms in different situations. And for the ability of KEPC-Push to handle potential popularity bursts, we can see that KEPC-Push's bandwidth utilization fluctuates less and its performance is more stable, which is what we expect. KEPC-Push can handle the potential popularity bursts and maintain a stable and higher peak period bandwidth utilization, thus achieving better performance. The more stable performance prevents edge nodes from experiencing overload and or idle states, bringing more efficient runtime. And to validate the role of each module, we designed the ablation study by replacing the FFE and the FDS modules with other alternative solutions and assessing the performance. Among all the combination schemes, KEPC-Push shows the best performance with the highest overall bandwidth utilization and the lowest cross-region request ratio. Shows that the important roles of the FFE and FDS modules. In summary, we analyzed the challenges of proactive push solution for edge-assisted video feed streaming and propose a knowledge-enhanced proactive content push strategy named KEPC-Push. KEPC-Push employs knowledge graphs to determine the popularity correlation among similar videos and push content based on this guidance. Besides, KEPC-Push designs a hierarchical algorithm to optimize the resource allocation in edge nodes with heterogeneous capabilities and runs at the regional level to shorten the communication distance. The experiments through production traces from Douyin platform demonstrate that both bandwidth cost and the user experience can significantly optimized. Okay, thanks